Good evening, everyone, and welcome to Astronomy Wednesdays with ICRAR and Astro 3D. Before we begin, I'd like to acknowledge that we are presenting this to you this evening from unceded Noongar land, and we'd like to pay our respects to the elders of the Noongar people, both past, present, and emerging. Now, you might be wondering, if you haven't tuned in before, what is ICRAR and what is Astro 3D? So ICRAR is the International Centre for Radio Astronomy Research. We are a joint venture partnership between Curtin University, the University of Western Australia, with some strong support from the State Government of Western Australia. And we exist to help do this we're about to talk about tonight, the Square Kilometre Array. It's behind me, the prototypes, you can kind of see, I've got a picture. And not only are we all about the Square Kilometre Array, we're also about multi-wavelength astronomy across all different kinds of light and basically discovering the universe. And Astro 3D is the ARC Centre of Excellence for all-sky astrophysics in 3 dimensions, and it unifies over 200 leading astronomers to understand the evolution of matter, light, and elements from the Big Bang to the present day. Before we get started with our talk today, I'd like to tell you about how you can get involved in some great astronomy citizen science yourself, and that's through a world record attempt that's going to be happening on June 21st. It's called World Record Light, and ICRAR is proud to be a sponsor. It's all about measuring light pollution. So light pollution obviously affects astronomy really badly. If you have a really bright street light and you try and set your telescope underneath it, you're not going to see many stars. But it also has environmental impacts and other wider reaching impacts. So it's really important that we know the levels of light pollution that are out there. And so this really great group have gotten together, the Dark Sky Association, and they're going to try and break a world record and measure the light pollution across the world, particularly in Australia, on June 21st. So you can join in at the URL that will be popping in the chat in just a minute. And you can register, and all you need to do is pop into your backyard with your phone and measure the light pollution at that night. Doesn't matter if it's cloudy or raining, they need every kind of measurement in every kind of weather. So look it up and join in. And now, without any further ado, I'd like to introduce our speaker for this evening, ICRA's esteemed Executive Director, Professor Peter Quinn. Welcome, Peter.
Hi, how are you doing?
I'm great. How are you enjoying your isolation this evening?
Surviving the isolation, I think, yes.
Now, before we get started, I'm really interested, Peter, if you had a world record, what would it be in? What would you want?
Maybe to be the oldest person on the moon. I don't know. I mean, I like to think there's still hope for me, so maybe that's the record.
Would you go to stay or just a visit?
Oh, very much a visit. Yes, very much a visit. I like my creature comforts on Earth much too much. Yes.
I guess they don't grow wine grapes.
They don't grow shiraz on the moon yet. No, sorry about that. No.
Well, thank you, Peter. I think that would be a pretty neat world record. I certainly don't want to be the oldest person on Mars, so I won't try and compete with you there. But without any more rubbish from me, let's talk about the Square Kilometre Array.
Great. Thanks, Kirsten, very much. Look, hi, everybody. It's a great to be here tonight to talk to you about the Square Kilometre Array. It's a very, very major and exciting international project that's obviously important for science, important for mankind, important for technology. But the most interesting thing, as far as we're concerned, is right here on our doorstep in Western Australia and also our colleagues' doorstep in South Africa. So just to give you some idea of what the project is all about, the SKA is a telescope, and like all telescopes, they're designed to show us the universe that we can't see with our eyes. So our eyes are very small things for detecting light, very small pupil that lets light in, and telescopes are all about finding a way of making our eyeballs bigger. How can we get more information into our eyeballs? And of course, the way that what was done basically was by Galileo, who was the person who discovered it, to use a telescope to cram more light into our eyes. So over here on the right-hand side is our eyeball, and we're looking at this thing on the left, which is kind of a cartoon of the entire universe that we see. Right up close to us, right near the eyeball, are things we see in the universe that are very close, the galaxies and the stars we can all see with our telescopes in our eyes. As we go to the left, we're actually marching out into the universe. We're going backwards in time to the very beginning of the universe, something like 13.7 billion years ago to the Big Bang. So that's the beginning of the universe, and we're at the other end of the story. We would love to understand this whole story as it unfolds and as the universe grows. One of the magical things about astronomy is we have that chance to do that, because astronomy and telescopes are kind of like time machines. As we look further and further out into space, the signals that reach us are taking longer and longer to reach us, and so it's like looking backwards in time. It's just like digging down on the Earth's surface. If you dig down a few inches, you find some McDonald's, and you dig down a few meters and you find some old Holdens, and you go down a few hundred meters and you find some dinosaurs. So as you dig down into the Earth, you go backwards into the history of the Earth. As you go outwards into the universe, as the light takes longer and longer to reach you, you're looking back into the history of the universe. So that's fantastic. We can actually go through, further we look out, the further back in time we're looking. Of course, the further you look out, the further things are away, and the dimmer they are, the fainter they are, because their light's spread out so thinly. So we need bigger eyeballs to be able to do that. So again, as I said, our eyeball, it's a little tiny pupil there. It's about 10 to the minus 5 of a square meter. It's very, very tiny. We can do better than that. We can build big eyeballs, and a telescope like the Parkes telescope, it's 1,000 square meters of eyeball, and that obviously collects a lot more information than our own eye does. And so it's able to see further out into the universe, further backwards in time. And things like Parkes do a really good job of seeing the things which are very nearby to us in the universe. If I want to go further and further out, so the little ladder on the bottom that goes from 0 to 1 to 10 is like distance. So if we want to get out to say distance 1, which is pretty far in the universe, more eyeballs are needed, bigger eyeballs are needed. So the way we do this is to add lots of telescopes like Parkes together and combine the signal that they get together. And so instead of having 1,000, say, square meters of eyeball, we have 10,000 square meters of eyeball, and that gets us about to distance 1 on this ladder. Great. The problem is we want to see further than that. We want to see back to kind of the beginning of this cosmic story. So if you look along the ladder to the left to that distance where it says 10, that's a particularly interesting place in the history of the universe. It's called the Dark Ages. So when the universe was very young and a big explosion, Big Bang occurred, the universe is very hot and expanding. Hot things that expand, cool. And as they cool, they form structures, just like clouds form out of steam. So as the universe cooled and expanded, the very first stars began to form. So until that time, the universe was completely dark. It was in the Dark Ages, we call them, and the very first stars began to shine as soon as the universe got cool enough. That's what we call first light. The very first stars that shone in the universe began there. We love to see that place in the universe's history, and all the stuff to the right, all that history, all that cosmic DVD of a story from the left through to the right, and we can do that once we get to this distance 10. So how do you get to distance 10? Well, you need more eyeballs, of course. So how many more eyeballs do you need? Well, unfortunately, if you want to go 10 times further away, you have to go 10 squared, which is 100 times bigger eyeball. So you have to add, instead of 10,000 square meters, 1,000,000 square meters. And 1,000,000 square meters is another name for a square kilometre. So if by some magical process we could gather together a square kilometre of eyeballs to look at the universe, we could reach back to this magical point in the history of the universe where the first objects began to shine. And that's page 1, chapter 1 of the cosmic story, and that was what we'd love to see. So the SK project, the Square Kilometre Array, it's not really a good name. It's not actually square, and it's not a kilometre by a kilometre. It's lots of dishes all added together that makes up a square kilometre of collecting area. But the Square Kilometre project has been around for some time. It's been around in people's minds and visions to get to this first light point in the universe for about 20 years or so. So in about 2011, the SKA organisation was formed. It was a UK company. Countries joined this company, basically. It was headquarters was in Jodrell Bank in the UK. The big telescope you can see on the left-hand side of that picture is the Lovell telescope, about 100 meters across, a very old, magnificent lady of radio astronomy in some sense. But this project began there about 2011. And Phil Diamond, the gentleman there, is the Director General of the project. A pretty important transition happened last year. So in March of last year, all the countries that were interested in the SKA said that they were going to form a new object, a new organizational structure called an intergovernmental organization. That's a much more powerful thing than just a company. It means that those governments at the cabinet level, at the government level of every one of those countries, they agree to join in a partnership that's long-term. They agree to give a certain amount of money per year to that enterprise. So, and it also facilitates travel of people without visas and without taxes. So it's an arrangement between countries to facilitate a particular project, an intergovernmental organization, very powerful thing. So in March last year, the first countries signed up to this. So this is the 13, now just gone 14 countries that have signed up to this. Australia, Canada, China, France, Germany, India, Italy, New Zealand, South Africa, Spain, Sweden, Netherlands, United Kingdom, and Switzerland. Switzerland joined very recently, just a few months ago. The ones that are underlined, and particularly the ones in the yellow, are ones where the whole process of ratification of agreement at the government level has been done. In fact, believe it or not, this morning we heard the news that South Africa had just completed the ratification process for the Square Kilometre Array. And so that's now basically all completed, all done, all signed. We need 5 of these countries to complete that process to start the new intergovernmental organisation, and we hope to achieve that by the end of the year. Australia is in process, and we hope to have their ratification through the Parliament by September, October. Now, as you can imagine, many countries around the world have other things on their table right now to worry about. SKA is probably not high on the list, but a lot of them are still very committed to try and get this organisation created and kicked off this year. There's discussions with other countries as well, Japan and Malta, Portugal, Korea, who also want to come into this fold. The overall sort of project timeline has been from 2013 to today, basically 2020. There's been a lot of construction designing the telescope, figuring out all the parts, how much the parts cost, who can do it, all the contracting, all that sort of stuff. What's called pre-construction process. There's about 200 million euros already been spent on that international, between these 13, 14 countries, designing the project and designing the telescope. Starting next year, we're going to begin the construction project. So the construction project, we're going to build two telescopes, one in South Africa, one in Australia, with the headquarters in Manchester. And that's about 1.7 billion euros worth of construction for the first phase of the Square Kilometre Array. So that's a very big international project for science, a very big enterprise, and getting all these countries to work together has been a major achievement. So what is the Square Kilometre Array? As I said, it's these two different kinds of telescopes. The telescope in Australia, which you see in the top left there, looks a bit like Christmas trees. These are receivers that they don't move. They're like antennae, like your TV antennae. They receive signals from the universe at low frequencies, at the kind of frequencies that you receive, say, from an FM radio station. So there are farms of these antennae. In this particular picture, there's about 256 of those little Christmas trees in this one patch, and there are 512 of those patches distributed over an area of about 100 kilometers by 100 kilometers. So about 130,000 individual little Christmas trees, all connected with fiber optics, all receiving signals from the universe in the low frequency part of the spectrum. On the right-hand side, you'll see the South African array. It works at a much higher frequency. It's a different kind of telescope. It works at about a 10-time higher frequency, about a gigahertz, the same kind of frequency as your mobile phones. And it's dishes. So these dishes move. They move to track things on the sky. The Christmas trees don't move at all. They move digitally, whereas these other things are moved by gears and cogs. The dishes, about 200 dishes, again, spread out over a large area in South Africa, in the Cape Province of South Africa, receiving signals from the universe, but at a 10 times higher frequency than the signals in Australia. And I'll explain in a minute why there are different frequencies. This is a bit technical, but I'll just try to give you some idea. It's a graph, and there are two graphs here. Up the right, the top left graph, you see sensitivity. That's how sensitive, how big the eyeball is, or how strong, how faint the signal is that you can receive against the frequency. The 0.1 is about 100 megahertz, about the FM frequency. The 1 gigahertz is about the cell phone frequency. And you can see SKA1, SKA2 are much higher up that graph by a factor of 100 or so than the existing telescopes, JVLA, the Jansky Very Large Array, LOFAR. These are telescopes that exist today. And so the SKA is going to be able to be between 4 and 20 times more sensitive than those previous telescopes. Similarly, this other thing down the bottom called survey speed. That's a very important thing for astronomy. It means how fast you can look at the whole sky. Obviously, if it takes you a long time if you've got a little tiny straw that you're looking through to look at the whole sky, it takes you many, many straws worth of observing to cover the whole sky. But if you've got a very wide angle lens, a very wide angle eye, you can cover the entire sky very rapidly. And so that's your survey speed, how fast you can survey the sky. And so you can see the SKA is again a factor of 10 to 100 times faster than looking at the whole universe than the current generation of telescopes. Just to give us some idea of the improvement of the images, on the right-hand side is kind of an image of a particular exploding star that comes from a telescope, the best sort of state-of-the-art radio telescope today. And you look at the one on the left, that's the SKA picture. So SKA pictures are like photographic quality. They don't look like radio telescopes anymore. They look like the kinds of images that you would take with an optical telescope. So a huge improvement in fidelity and resolution and sensitivity to look at the universe. You might be able to read all of this. This is the timeline of the SKA, but basically those big blue bars on the bottom, they start about the middle of next year. That's the beginning of construction. And that construction period, building the infrastructure and the networks and the dishes and all the other things, runs for about 6, 7, 8 years. So towards 2027, 2028, we're going to be seeing enough of the telescope assembled to start doing scientific observation. So by the end of this decade, we'll have a full up, all singing, all dancing SKA in both countries and doing all the science we want to do. So it's not going to happen overnight. It's a very big engineering project. One of the world's largest fiber optic networks needs to be built. The world's largest telescope needs to be built. The world's largest observatory needs to be built. We're talking hundreds of people working for many, many years to achieve this, but we're on the verge of starting the construction of this project. I want to say a bit about WA. So WA is a unique place. We have lots of interesting things here. We have some of the world's best grapes, right? Best wine in the world. We have big holes in the ground where there's all sorts of interesting things come out of those. And we have great beaches. We have these beautiful, unique resources that we have. South Africa is quite similar in many ways to this, actually. But the one thing we have is a lot of this nothingness, right? You go for miles and miles and miles and miles with nothing. That magnificent isolation that we have here in Western Australia produces some of the radio quietest places in the world. So you can imagine if these telescopes are trying to listen to the universe at the same frequency as an FM radio station, then if you're right next to an FM radio station in a town or a small village or whatever it is, you're not going to be able to look at the universe. It's like having fog or equivalent of fog in the radio. So further away you are from people and FM radio stations and TV stations and all those things that broadcast radio, the better off you are. So we've got this beautiful Western Australian desert, Western Australian isolation, which gives us this incredibly sharp and quiet view of the sky. And then, of course, the quieter it is, the fainter the thing you can hear. And so looking at the edge of the universe, it's the greatest place in the world for it. Just to give you some idea, this is these are sort of plots that show on the y-axis, on the vertical axis, the signal strength, and on the horizontal axis, the frequency. And so if you point the telescope at the sky, this is kind of the signal you see. It's just very, very flat because there's no interference, there's no spikes, there's no rubbish, no noise coming from FM radio stations and things. The only thing that's there in this particular picture is a bit of a dip, and that's actually coming from a distant galaxy. Right? So that's a signal from a distant galaxy. So we've got this beautifully quiet, flat, noise-free spectrum to look at the universe with, which is a fantastic asset of the Murchison Radio Astronomy Observatory. Over the course of the time that I've been in Western Australia, I came here about 2006, and all that period of time, there's been an enormous investment in Western Australia for the SKA. Even before the SKA site decision was made in 2012, that decided to put half the telescope in Western Australia. The Australian government and the West Australian state government and the universities in Western Australia all decided together this was such an enormous opportunity for Australia and for the state that they would start investing. So over that period of time, as a precursor, as a pre-investment, as a, if you like, in improving the quality of the Australian site, lots of things were done. The International Centre for Radio Astronomy Research was founded. The Murchison Radio Astronomy Observatory was done. 2 radio telescopes were built. Desert fibre optic networks all the way from the desert up in the north down to Perth were built. Supercomputer centres were built. All this was done even in advance of deciding that the SKA was going to come. So that was about $500 million worth of investment, and that's mostly federal funds that came into Western Australia. And so that's an enormous international investment, by international scales, that's an enormous investment in science, and it's happened here in Western Australia. And it's had a huge impact on what we can do here in Western Australia and Australia in general in terms of astronomy. In 2015, this federal government said, oh, and by the way, here's another $300 million, which is Australia's share of the construction fund at that time. So we very early in the project said, we're very serious about this. We're going to put our money on the table right now. That's our share of the amount of money that's needed to construct the telescope. Today, that share is, since things have got more expensive over time, it's about $380 million, but we'll get about 70% of that back. One of the nice things about a big project like this is if you're a partner in the project, you get a return on your investment. And so Australia gets back in terms of contracts to Australian companies and Australian organisations about 70% of that investment. And in fact, there's even more investment than that. So of course, SKA Low is going to be built in Australia. That SKA Low telescope costs about 560 million Australian dollars. And of course, that's going to be spent mostly in Western Australia. And so people are going to be employed. Hundreds of people are going to be employed to build this telescope and to be able to get it online. And of course, once it's built and working, it'll be operated, and it takes about $65 million per annum, not $65 million per year to run the telescope. And again, most of that money is going to go into paying bills in Western Australia, paying people's salaries and power bills and all sorts of other bills. So, you know, this is a very important investment for Australia and Western Australia, but it's also the world's amazing, world's first and leading scientific instrument. So I want to show you a little bit about what the observatory looks like at the moment. So this is some images that were taken as a video, which is taken in 2020, and I'll talk a little bit over this video. Just to orient you a little bit, that white circle, white outline there is the Shire of Murchison in Western Australia. It's an amazing place. There are no towns. It's about 120 people live in that white area up there, just about 300 k's northeast of Geraldton. For comparison, that's the Netherlands, which is European country, as you know, with a lot more than 120 people in it. And so it's a very large piece of land with a very, very, very few people in it. And I love to show people from overseas this picture as well, because it just emphasizes to me how big the state we live in is. And this isolation is a huge, huge asset for us. So this video will show you some of the things that are going on the site, and it's taken very recently. So again, just to orient you, here's Western Australia, and we're going to zoom into the Murchison Radio Astronomy Observatory. There are, as I said before, there are two different telescopes, what they call precursor telescopes on the site. These test out the various technologies of the SKA. So as we fly in to the site, those white things you see there with the dishes are what's called the Australian SKA Pathfinder. This is a dish telescope. It's a similar telescope to the South African telescope that's been built for SKA. This has a very, strength of this telescope is has a very wide angle field of view. It's a very big survey telescope. There are 36 of these dishes, each about 12 meter in diameter. And at the apex of each one is like a digital camera that works in the radio part of the spectrum. So it can take these amazing pictures, and I'll show you some in a minute, of the whole sky pretty much in the radio part of the spectrum. The second telescope that's there is the Murchison Wide Field Array. These are like the Christmas trees, where they look more like spiders than Christmas trees, but bat wings or whatever you want to call them. But these again are a low frequency, 100 megahertz-ish radio telescope that don't move. And this is a precursor, a initial version, if you like, of the Christmas tree-like array. So both of these precursor arrays have been up there, and they're operational scientific instruments. The control building is very special. As you can imagine, we take lots of computers to run these telescopes, but of course computers generate noise, so you can't have that noise get out there. So we've got the equivalent of air locks, which are radio locks. So this is in a shielded building, doesn't allow all the signals from the computers to go outside. There's no power lines going up to the site, so it's not on the grid. So in fact, we have to generate on site the power. So this is a very large solar array that collects solar energy. It charges up batteries, and this is one of the largest batteries in Australia. It's about 2.5 megawatts of battery. And then we have diesel fuel, which helps during the evening to power the telescopes. Also on the site, we're doing some of the early work for testing the real design of the SKA. So one of the very first designs for the Christmas tree is this one here. We have set up one of the farms, 256 of these guys in a farm, to be able to test out how well they perform as well. So this is like a laboratory. It's, as well as doing science on the MRO, it allows us also to do some of the early testing. So let me show you some of the things that these telescopes have been doing. Here's the Murchison Wide Field Array. It works from about 70 megahertz to 230 megahertz, so it's in this FM kind of region. But it's a working scientific instrument as well as being a precursor. And it's taken some rather amazing pictures of the sky. So this is a picture of the radio sky. This is almost the entire horizon to horizon sky. The band you see in the middle is the Milky Way. But this is taken not with the light that you can see with your eyeballs, but the low frequency radio waves. And you see the galaxy looks very different. It doesn't look like, the big emu we can see in the sky with our eyes. It looks very different. We see different kinds of objects. We see the gas, primarily the hot and warm gas of the Milky Way galaxy, some of the energetic particles in the Milky Way galaxy. We see distant galaxies. The thing that looks a bit like a banana up there in the top right-hand side is in fact a distant galaxy, a very powerful distant radio galaxy. So all this is telling us lots of things about the universe, but in a way we can't do with our eyes. And this wide-angle picture is an amazing panorama that's taken with the Murchison Wide Field Array. With ASCAP, the dishes of ASCAP, I told you before, it's also very good at looking at wide angles, but it's a different kind of telescope. It works at a higher frequency. In fact, it works at the frequency of the hydrogen gas that dominates our galaxy. Most of our galaxy the gas is hydrogen gas in our galaxy. It emits a particular radio frequency. And so if you look at our galaxy and nearby galaxies, you see the emission of the gas, of this hydrogen gas. So this is a beautiful picture of the Small Magellanic Cloud. So this is a galaxy which orbits our own Milky Way galaxy. It's full of gas, and this is a picture of all that gas, and it's all bubbly and frothy and foamy because the stars are pushing all that gas around all the time. And that gas is what the stars themselves are eventually made out of. So it's again a way of looking at the star-forming material, this hydrogen gas and nearby galaxies with a beautiful resolution. And the full moon on this picture is about the size of one of those bright spotches in the middle. So this is an enormous piece of the sky that this telescope's able to look at one time. And of course, our colleagues in South Africa, they're also building the precursors of the mid-frequency, the high-frequency, mid-frequency SKA. So this is called, the telescope is called Meerkat, not named after the animal, of course, but CAT means Kourou Aperture Array Telescope, and MEER is Afrikaans for more, so more of those. So there's 64 of these dishes down there called Meerkat. These are a little bit larger than the ASCAP dishes, and they work at similar frequency to ASCAP, but they look in a very narrow angle. They're not the wide angle of the ASCAP telescope. They're a very narrow angle telescope. Again, very sensitive, very powerful telescopes, and they can also produce images of the sky. And so this incredible picture here was made with the Meerkat array. It's looking at the very heart of the Milky Way galaxy. So this is showing you a lot of the hot gas that's in the Milky Way galaxy. And we think there's like a black hole right in the middle of the Milky Way galaxy. So all this streaks and filaments and bubbles and things are all associated with the activity in the middle of the Milky Way that surrounds the black hole that we have in the middle of the Milky Way galaxy. So it's a beautiful picture. Again, beautiful, high, almost photographic kind of quality picture. One of the other great things that's happened in Western Australia, as well as the precursors being built and the Murchison radio astronomy being built, observatory being built, is of course ICRAR. ICRAR is the International Centre for Radio Astronomy Research. It's a joint venture of the two big universities here, Curtin University and the University of Western Australia, with a lot of state government support. We now have over 200 staff and students that have come from all over the world to be here at ICRAR over the last 10 years. We've published a couple of thousand papers. We've raised about $85 million in grants. We've, talked to about 160,000 people in the community. We are a major international centre that's grown up here in Western Australia from basically zero. We're now within the top 5 centres of our kind in the world. And we are here to anchor, to deliver, to make sure that some of the returns, all the kinds of returns, the educational returns, the science returns, the economic returns of the SKA stay in Australia, and in particular in Western Australia. And just the remarkable stat that I have is basically when I came back to Australia, most of the astronomy community in Australia lived on the east coast of the country. Now a third of the entire community of astronomers in Australia lives on the west coast. So that's an amazing shift in the demographic of science in Australia just over that 10-year period. ICRA's been involved not only in doing science, but also helping build the SKA, so helping design the various parts. So all these boxes around this picture, all the various components, if you like, of the SKA, the telescope manager, the low frequency Christmas trees, the science data processor that does all the computing, the assembly integration, the mid-frequency array, all those are bits and pieces that you would have to design and build to build the entire 2 telescopes. So ICRA has been working very hard on this low-frequency aperture array, on those Christmas tree-like designs, because we're here on the ground in Western Australia. We've got a great opportunity to be able to go up to the site, try ideas, come back with results. So we're on the spot, which is very good. We've been working also with the science data processor, and in fact, we're responsible for designing a big part of the science data processor here in Western Australia, and I'll talk more about data with the SK in a minute. And we work with companies, we work with other countries around the world, and we work with big companies. We work with the IBMs and the Intels and the Amazons and various other companies to help design some of these very important systems. So data is it's the lifeblood of the SKA, it's the lifeblood of all telescopes, but the SKA breaks all the rules, it breaks all the records. So if I look at a big radio telescope today, like the ALMA telescope, which is at the top of this picture here, it produces about 1 petabyte of data per annum. Okay, so that's 1 in 15 zeros, right? So that's a lot of data. It's 1,000 gigabytes of data, and 1 million gigabytes of data, pardon me. And so, it's a lot of data by our standards as humans, and that's what it produces. If you go down a bit further, you see the SKA is going to produce something like about 300 times to 700 times more data than that telescope. So it's almost to what's called an exabyte of data a year. That's 1 in 18 zeros, 1 billion gigabytes, right? So that's kind of equivalent to the amount of data that's running around the internet today, right? So this telescope is almost like another internet by itself. And it's an incredibly big challenge, of course, obviously, as scientists to be able to harness that data and do science with it. So the data challenges of the SKA are significant. So this little cartoon kind of typifies to me how we're going to try and deal with this, right? So this has got these beautiful telescopes that gather all these noughts and ones from the sky, and they flood in, and they very quickly fill up all the dams and the buckets and the swamps and the lakes and whatever we've got to throw at this collection of data. We fill it up very quickly. So we've got to figure out how to manage all that data and get it to the people who want to do the science with it. The SKA project, so this is a sort of a change of the way astronomers have worked. So on the top here, the traditional way of working was, you'd go to your telescope, you'd take some data with a bring it put on a magnetic tape, you'd bring it back to your home university and you'd analyze it. When you're dealing with something like the SKA, the thing in the middle now is no longer your desktop at home or in your office. You need the world's biggest machinery to be able to deal with this data. So you actually have to, somehow or other, an individual person has to be able to reach out and use some of the very largest machines in the world to help them deal with the science data that they want. The challenge we have is that the SKA project, so building the telescopes, the 2 telescopes, is being paid for by the construction budget, and that's been agreed to. And that's the top part of this picture, the big dish with all the numbers coming in. The bottom part, all this infrastructure to move data around and to process it, that's something the community is going to have to do. The community is going to have to gang together around the world and figure out how to put all these sort of numbers in the right places and process it. So it's going to be a community effort. This is not unusual. There are other projects around the world that have done this, like the Large Hadron Collider about 20 years ago. We want to do it today. Things have moved on a bit. We've got the cloud computing, we've got all sorts of technologies, but we the community are going to have to deal with this. And so we're going to have to put together what we call SKA regional centers around the world. These are regional centers for computing and data processing that receive the data coming from the 2 telescopes, process it and give it to the scientists, and let the scientists then basically do the science with it. So we have to figure out how to put this network together, where's all the data going to be, how's it going to get from place A to place B, et cetera, et cetera. So we have to design and build this network of data systems as well as the telescopes that produce the data in the first place. And that in itself is a very challenging problem. There are lots of projects around the world. There's about probably 9 or 10 projects around the world, the Aeneas project, ESCAPE projects in Europe. Here in Australia, we have the Australian SKA Regional Centre project. We have a joint project with China called Eridanus. There's lots of people around the world who are already working on how to put this network of regional centres together to be able to address and capture and deal with all the data coming out of the SKA. Just to give you some idea of how challenging this is, we had a chance to try out some of the ideas just recently. So suppose somebody magically, the SKA was built and the SKA is pumping out data. Could we even our current systems, our current software, our current methodologies, our current algorithms, would they even work at something that big? So we have here at ICRAR a very strong relationship with the Oak Ridge National Laboratory in the United States, which is the home to the Summit supercomputer. The Summit supercomputer is the world's largest computer. It's 200 what's called petaflops. The Pawsey Center in Perth is about 2 petaflops, so it's about 100 times bigger than the Pawsey Center. It's about 220 million euros worth of computer that chews up about 24 million euros worth of power every year. So it's a big monster computer. But we were allowed to do some experiments with it to test out how we would deal with the SKA. So what we actually did was, on the left-hand side, we actually simulated the sky. We built a model of the sky. We then built like a software telescope and observed the sky and generated in about 3 hours of Summit time, about 6 hours worth of observations from the SKA. So we synthesized, we created, we modeled, if you like, an SK observation of the sky that took about 6 hours. And then we were able to process that. There was about 400 gigabytes of data per second. Okay, that's about 100 or so DVDs per second worth of data coming through this thing. And we're able to process it and analyze it with some of the software we had, and then actually produce at the bottom of this whole thing a picture of the sky, which is the one we started with. So in other words, we went all the way through of modeling the sky, producing a picture, telling the telescope to produce the same picture, and it did. So we need to do this kind of stuff with the world's biggest machines, because we have to have the ability to model and synthesize and test some of our ideas. So that's the sort of work we're doing here in Western Australia at ICRAR. We're doing some of the world's largest data science problems, and the SKA project is a project that's generating this kind of interest. It's generating interest from companies, it's generating the ability to train people in data science, and it's generating all sorts of other skills. I'll leave you with another video. I like this one very much because it shows some wildlife, which I like very much. It's the most recent work that's been going on with our Italian colleagues. It features some of the telescopes you've already seen. This is the Murchison Wide Field Array again, but some of the most recent generations of Christmas trees. So as we go and fly over the site, this was taken very recently, you'll see some of the most recent developments. So here's one of our local friends who's very friendly, but he likes telescopes too. And this is the old Christmas tree version. This is the original one you saw. That's now basically been bypassed by a new generation of Christmas trees, which are these ones here. This comes from the Italian collaborators. This is an Italian designed Christmas tree array, again with our friend checking it out. And it is producing very nice results. We're going to build 256 of these guys on one of these farms to be able to test out again whether this more advanced array, you can see some of these patches of the arrays here on the desert, how it works. It gives us a chance to train our engineers, to train companies. So some of the companies that are going to be involved in installing this 130,000 Christmas trees that can be out there and getting some practical experience with it. We've also laid out some more of the little butterfly kind of ones as well. So the Murchison Radio Astronomy Observatory is a fundamentally important place for the SKA. It's our laboratory, it's our test bed, it's our training ground for our students, and it's where we're going to figure out how to build the SKA in the end of the day. So that's it. The SKA is happening. You can see stuff, touch it. It's all good. You can see in Kirsten's background there. It's all happening. And it's a great chance for Western Australia to grow scientifically, technically, to grow our skills and grow our challenge, grow everything that we're doing here in Western Australia, diversifying our economy. But it's also a great chance for all of Australia to be part of one of the world's best science projects. Thanks.
Thank you, Peter. It's been so exciting to see this project develop from the site decision and just year on year see more and more happening. And now we are really at the pointy end and construction is so close. Really exciting.
Yep.
If anyone has any questions for Peter, please type them into the chat box below the video or to the right to the video, depending on how you're watching it. We have had a few questions come through during your talk, Peter. So Lucy Zhong asks, why is the SKA not built in a Y shape like the VLA?
So when you look at the kind of array that you need for a particular kind of science, it's different. In other words, the SKA was built with a particular science in mind, a particular kind of observation, a particular kind of fidelity of the image on the sky. How the dishes are laid out kind of determines how fine-grained your image is. So if you lay them out like in a spiral pattern, it's like the optimal pattern. And of course, the VLA at the time didn't have enough land to do the spiral. They had just a small amount of land to do the Y kind of array. So the better choice for the array is in fact the spiral-like arrays. Again, it depends upon the science that you want to do and what fidelity you want.
Thank you. Grant Boxer also asks, and you might need to flick back to a slide for this one. Mm-hmm. You showed two pictures, one from LOFAR and one simulation of what the SKA would see. And he asks if that's the Crab Nebula.
I know the picture. I think it actually is. I think it is the Crab Nebula. I won't be held to that, but I'm pretty sure it is. Okay.
It looked like it to me, but I'm no expert.
Well, I'm not an expert on the radio images of the crab, but I think that was.
Another question from John Cooper. How are the antennas going to be assembled? Are they going to be assembled in WA or elsewhere?
So, IKEA flat pack kind of technology. So the antennas will be shipped on board on shore in parts and assembled in Australia. Basically, the parts will be manufactured probably all over the world in various places, but they'll be assembled here in Australia. And that's what having those antennae up there right now gives a lot of people a lot of chance to figure out how to do that optimally. How do you put 100 together and ship them all out to the site together, or do you one at a time? What's the best way to do that? And so we get a lot of chance to practice, but we will be assembling them in Australia.
Another question about the antennas from Grant Boxer again. What's the purpose of the mesh underneath them?
So the mesh underneath is what's called a ground plane. It basically sort of protects the telescope a little bit from currents. Because if there's a lightning or if there's various kinds of activity in the ground where there's currents flowing around, it's like an electromagnetic shield. It stops signals coming up from below, from underneath the ground in some sense. So it's like a protection, like a shield, if you like, for radio signals coming from that direction.
And I think our final question, unless some latecomers come in, is from Ian Kemp. He asks, it will take a number of years to build the SK, as you've said, but when will the data be available for scientists to use?
So it's one of the nice things about building an array of telescopes. In other words, you're going to build 130,000 of them. you can build 10,000, you can use that 10,000 to do the first observations, and then you build some more, and you build some more, and you do more observations. So we hope to have enough of the telescope in place to start taking data by the middle of this decade, by say 2025, 2026. It won't be the full array, it'll be test data in some sense, but that'll give us our first feeling for how well the telescope is performing. And then, of course, it'll grow from there. So doing the largest pieces of work the telescope has to do, doing these very large surveys, looking for the first light, looking for that magical signal, we won't have enough telescope in place until probably the end of the decade to start doing those surveys. Okay, so that's going to be something that's going to take a while to get there because it requires the entire sensitivity of the whole telescope.
What kind of science do you think will be accessible with the interim telescope along the way?
I think it's very good at looking at that sort of intermediate zone between sort of the Earth, if you like, and the nearby universe. It's got enough sensitivity to look at that intermediate zone and find signals. So, you know, the gas, the hydrogen gas, not just from the nearby galaxies, but for galaxies that are much, much further away. So it's going to be looking at a census, if you like, of nearby galaxies, and you know, probably a billion or more, I say galaxies, maybe a billion or more galaxies, but doing a census of the gas emission from those nearby galaxies. And they're not at the edge of the universe where the first stars are formed, they're relatively nearby, but when you've got, you know, the early telescope in place, you can start building that census.
We have two final sneaky questions that have snuck in. One from the Nerdy Walker, who's asked if it's going to be possible to use quantum computers to analyze the vast amount of data.
Quantum computers are interesting. They're really, really, really fast at doing problems, but the problems they do work on have a very small amount of data usually. So they're on the Ferrari kind of, you know, they work very fast, but they're very small. And so they can't deal with all the data volume that the SK has. Its biggest issue is data volume. Okay, and it also has data processing as a problem, but it's data volume. So quantum computing is interesting, but it's probably not the optimal kind of computer to use on the SKA.
John Cooper also asks a very astute question, I think. Is there a possibility of setting up antennas remote from the Murchison to improve the resolution? There must be other areas available in Australia, he notes.
A very good question. Yeah. So the original concept for the SKA was exactly that. So when we first designed the SKA, we imagined the Murchison radio astronomy observatory being the hub, being the nucleus, and then dishes, antennae being sprinkled all the way across Australia, maybe even all the way over to New Zealand. That vision, that dream is still alive. It costs a lot more money than what we've got, but it's absolutely correct. The wider you spread the dishes, the higher the resolution, the finer the picture you can make. And so, yes, I think people will be very interested in doing that, but not in the first phase of the construction.
Awesome. Final question from Roger Groom here. There's a large contingent of astronomers associated with ICRAR. Is ICRAR also expecting to have a strong representation of data scientists and or software engineers working on the project in WA?
Absolutely. So ICRAR has been built around three things. It's been built around the astronomers and doing the research work. It's been built around the engineers, the people who actually design the electronics and get out there into the field and do stuff. And it's been built around the data scientists as well. So we have all three flavors of researcher here in ICRAR already, and that'll grow over time. But as the SKA comes online and as the data starts to flow, even now with the precursor data, we're a fantastic training ground for young people who are interested in data science. So we've already got a large number of our students who are going off and doing careers in data science as well as astronomy.
Fabulous. And look out for jobs at ICRAR. We're always advertising. In fact, we've got a job advertising right now.
We have jobs all the time. So we're here. We've just been funded for another 5 years of our work, thanks to the state government and the two universities. So we've got a very strong work program in place between 2019 and 2024. We're in our third 5-year program, and that's going to go right out into the SK construction phase.
Hopefully we'll see you working for us.
Thank
you so much. Thank you so much, Peter, for giving us an SK update tonight. And thank you so much, everyone, for joining us on our channel. This week was our second last talk. Next week, we'll have our last in the Astronomy Wednesday series with Dr. Savina Velstedt, who will be sharing with us some more talking about galaxies and the evolution and how they've changed over time out there in the universe. So we hope to see you next week. Otherwise, have a great evening and we hope you stay safe. Thank you so much for joining us.
Thanks, Kristen.